Hello, good morning, good afternoon, and good evening. My name is Jason Joseph. I'm a postdoc at Rice University, and it is both an honor and a pleasure to speak in this seminar. So thanks very much for the invitation. And today I'm going to be telling you about meridional ranks and bridge numbers of knotted surfaces and welded knots. So let's begin. So this project is joint work with Pudipong Pongtanapaisan from the University of Saskatchewan and some background. So I guess the starting place for all of this is the meridional rank conjecture for knots in the three-sphere. So let me, it would be really silly to talk for an hour about that without saying what the bridge number is or meridional rank. So it's the minimal number of maxima over all embeddings with respect to the standard height function. So here you see two maxima in this embedding that turns out to be optimal. And you could also consider a few related things. So there's this overpass number. So these are overpasses. Actually, they're all overpasses. There's 4 overpasses in this diagram. But it turns out that for a classical knot, the overpass number is equal to the bridge number. So there is some diagram with only 2 overpasses. And the bridge number is equal to the Vertinger number, which was defined by Blair, Kuchikova, Velasquez, and Villanueva. I will define it later on. We're not quite to that point yet, but the bridge number for classical knots turns out to be equal to several other things, so that theme will be important. Also, nice fact about the bridge number is this -1 additivity, sometimes called Schubert additivity, because Schubert proved that this formula always holds the connected sum. You get the sum -1, because you take the 2 maxima and just kind of fuse them together when you do the connected sum. So that's great. What is meridional rank? It is the minimal number of meridians that you need to generate the knot group. That's the fundamental group of the exterior. So here's a little picture of a meridian. So your knot is out there in the world, and it has this normal 2-dimensional normal bundle. So there's a little transverse disk at every point of the knot, and a meridian consists of the boundary of that disk together with a tail to the base point. And the set of meridians forms a conjugacy class always. All meridians are freely homotopic. So some quick things about meridional rank: it's always finite, and one proof of that is the Vertinger algorithm, which from a diagram, you label the arcs with symbols which correspond to meridians around that portion of the knot. And at each crossing of the diagram, there is a conjugation relation. And if you write down those generators and those relations, that gives you a presentation for the knot group. And if your knot is in bridge position, it's not too hard to see if you take a meridian to each of the maxima, they will generate the knot group. So the meridional rank is a lower bound. See, after those two little bridges, it's just a braid, and then they meet up at the bottom. So those two meridians will generate, and meridional rank conjecture is about whether or not this is always true. But first, this is a convenient time to say what the Verdinger number is while we're talking about the Verdinger algorithm. So my dog is snoring on the couch. All right, so Verdinger algorithm, if you have the overstrand and one of the understrands, you can solve for the other understrand. It'll be like some conjugate of the first understrand by the overstrand. So the Verdinger number is the minimal number of seed strands needed to complete the Verdinger algorithm. So let's do an example. So here's a virtual knot, and let's choose this very long arc, and I claim that that's the only one that we needed to color the rest of the diagram. So looking at this top crossing, I can color this understrand. Now I can color this one. And now I can color this one. So in this diagram, I only needed one seed. So the Verdinger number here is 1. Now, a couple of things in this diagram, the number, so B sub O is like the overpass number. There are 2 overpasses, and the number of maximums is 3. So these can all be different. And Verdinger number, you're supposed to think is sort of like the most efficient or combinatorially like practical from this example. So the people I mentioned before, Blair, Kuchikovo, Velasquez, and Villanueva, proved, well, they defined the Verdinger number and they proved that it always equals the bridge number for classical knots. So this is a very cool theorem, and it led to them computing the bridge numbers of 50,000 knots or something. So it's useful. And that said, let's move on. So the meridional rank conjecture, we already said, is meridional rank always equal to the bridge number? It's always less than or equal to. Is it always equal to? And so this is open. Considerable progress has been made. So there's a lot of families where it's known to be true, but still very much open. So a small survey that I do not claim is complete, it's certainly not, but it's some of the most familiar families that I'm aware of. So it's true for 2 bridge links, pretzel links, Montesinos links, which generalize both of those, twisted links, which generalize pretzel links, and certain kinds of arborescent links. So that's what the stars are about. And I'm gonna not get into the details really, but a lot of arborescent links. And so I put some of the authors, oh, I forgot torus links over here, and more. So this was Rost and Zisheng. Montesinos links was Bolio and Zisheng. And these two big families up at the top was Bader, Blair, and Kuchikova. And what were the techniques? Well, we'll get to that later. I'm not going to say that yet. But the motivating question is, to what extent is the Meridional rank conjecture a reasonable conjecture for other knotted objects, such as knotted surfaces and virtual or welded knots? When and how can we prove equality, and can we find inequality? So maybe one thing to point out is that you can hope to prove the Meridional rank conjecture for classical knots by proving it for a bunch of different families. You can hope to exhaust all knots like that, and there you go, proved by cases. There's really no hope of doing that for knotted surfaces because we can't even exhaust all of the knotted spheres in any way whatsoever. There's probably never going to be a complete list. That's what I think anyway, but that doesn't mean it's not, fun to sort of see what you can prove and worthwhile. So a lot of what this talk is about is taking techniques that worked for classical knots and seeing, do those techniques work for sort of knotted objects that came from classical knots in some way. So you'll get a flavor of that as we go on, but that's sort of the point. And of course, you could hope to disprove it. You can hope to find an example where the Meridional rank is strictly less than the bridge number. So we have something to say about a potential family of counterexamples that, of course, we can't prove are counterexamples, but I sort of believe that they are. Great. Any questions? Okay, so virtual knots. See, I didn't put in the title because depending on your definitions, Meridional rank conjecture is false for virtual knots. So, so what do we mean by bridge numbers? So I like to just have, sort of a height function on the page, R2, and count the number of maxima. So to me, this is bridge number 2, and so is this. However, notice that this one on the right has only one overpass. And if you play around with the Verdinger algorithm, you'll see that means that the group is Z. Okay, so Z is generated by one meridian, always. However, this has a non-trivial Jones polynomial. And so this, in terms of the number of maxima that you see, has to have at least two. If you have only one, then you can just do Reidemeister 1 moves and virtual Reidemeister 1 moves and just simplify down to a crossingless diagram. So it's a non-trivial virtual knot. That means that it has B sub m at least 2. And here we see it, it is 2. But the group is Z, so Meridional rank is 1. So that's why I threw virtual knots out. However, whenever we compute the bridge number and the Meridional rank to be equal for a welded knot, which I will define in a second, we're also showing that it's equal for at least one virtual knot, probably a lot, but you know, it'll make sense to say this part first. So welded knots are a quotient of virtual knots where you allow one additional Reidemeister type move. And therefore, if you have some welded knot and you know its bridge number equals its Meridional rank, well, the diagram is also representing a virtual knot. And so that particular virtual knot also satisfies those properties. But anyway, that's why I said welded knots in the title, and I sort of like them better anyway, because they have more of a connection to knotted surfaces, which we'll talk about. But also interesting to note that as a welded knot, this is equivalent to the unknot. So it doesn't, break the Meridional rank conjecture for welded knots. That is still open. Okay, so a couple of things about all these different notions. So we just said that the overpass versus the number of maxima can be strict, can be distinct for virtual knots. For welded knots, it was actually proven that they're equal by Nakanishi and Sato. So that is kind of good, in my opinion. And similar to how the Verdinger number is equal to the bridge number for classical knots, in a previous work, Udipong showed that the Verdinger number is equal to the overpass number for virtual knots. And in this project, we also showed that that's true for welded knots, although I think that's really a corollary of Udipong's previous work. But anyway, it's good to point out that it's true. And this means for welded knots, I can just say the bridge number, and I mean all of these different things, they're all the same. So that's what I mean by the bridge number of a welded knot. And thinking about it in different ways can be helpful at different times. What's the meridian of a welded knot? Well, you can define it diagrammatically using the Verdinger algorithm, or using the tube map, which associates a knotted surface to a welded knot. I'll explain that soon. And so that's it for my welded knot introduction. Knotted surfaces will be mostly orientable in this talk, although there's one part where non-orientable comes up, but what's the bridge number of a knotted surface? Well, it should just be the minimal number of maxima over all embeddings with the standard height function from S4 to R. And meridians is really the same definition as before. You still have a two-dimensional normal bundle, codimension 2. So that's all the same. At every point of the surface, there's a little transverse disk, right? So some of the examples, because they're kind of hard to draw, it's sort of better to just define them. Twist spun knots. So Artin introduced spinning, which is where you spin a knotted arc in a 3-ball around its boundary 2 sphere, sweeping out S4, and that arc sweeps out a knotted sphere, kind of like a jump rope with a little knot in it, and the jump rope is allowed to like go through the 4th dimension. So that would sweep out like a sphere, and if the rope is knotted, it sweeps out a knotted sphere. So what you can do is twist the knot as you spin some integer number of times, and this gives you the m to a spin of k. And another picture. So if you just spin halfway, then in S3 on the top here, you'll see the knot connects on its mirror, and this disk stretches down into the 4-ball. And so this is the standard ribbon disk for K connects on its mirror, and take 2 copies for that and glue them together, and that is the spun knot. And so if instead of just gluing them in a sort of a doubling fashion, if you glue them by a diffeomorphism that twists the boundary, that's another way to understand a twist spun knot. And that way, I think, makes the bridge number a little bit easier to understand, because in this half spun disk, what are the minima? They are the index 0 critical points of the knot in B3. So minima become 2-dimensional. 1-dimensional minima become 2-dimensional minima. So that means the bridge number of the twist spun knot is at most the bridge number of the knot that you're spinning. So that's all good. So kind of, when is it equal? Is it ever not equal? That's one thing we should think about. And on the algebraic side, for any twist spun knot, there's a surjection from the classical knot group to the group of the twist spun knot. And it's given by forcing the meridian to the mth power to be central, so to commute with everything else. And you know, if you have some meridians here, they'll generate the quotient. So the meridional rank is potentially smaller for the twist spun knot. When does equality hold? So there are a couple of kind of dumb cases that should be mentioned. When it's just a spun knot, no twisting, the groups are the same, the meridians are the same, so the meridional ranks are the same. And when m is plus or minus 1, and like only in those cases, the one twist spin is always unknotted, so it has meridional rank 1. So it makes sense to ask, except for these sort of silly cases, can this be strictly less? So I don't know any examples of that, but we do have examples that I'll say at the end, where you have a connect sum of twist spun knots, and the meridional rank of the connected sum is strictly less than that of the connected sum of the knots being twist spun, but notice these twisting indices are different. They were the same. Connected sum of twist spins is a twist spin of the connected sum, so that wouldn't really work. But if you allow yourself to change the twisting indices, you can make some funky stuff happen with the algebra, with these relations. Okay, so that's one kind of example and some motivation. Another is ribbon surfaces. So start out with an unlink of two spheres. And then join them together by a bunch of tubes. And if you've just joined them all, then that will be a ribbon sphere. And if you attach additional handles, then you just raise the genus. So this is analogous to ribbon knots in S3, the bound ribbon immersed handle bodies. And they're a nice class of knotted surfaces because you can just write down a presentation and then go build a surface that realizes it very easily. Usually, if you're looking at a knot group and you want to find a knotted surface with that group, it's very non-obvious. There aren't really a lot of techniques to do things like that. But for ribbon surfaces, it's super easy. So notice the number of spheres here is an upper bound for both the bridge number and the meridional rank. A meridian for each of the spheres will generate, and also those are the minima or the maxima. So there's a connection I should mention with the welded knots where Yajima was the first to do this, where you take a classical arc or a knot and you tube it. So it makes a ribbon surface, and he noticed that the group was the same as that. The group of the complement of the knotted surface was the same as that of the classical knot. And let's say tube of K. And Roseman was first to show that this is actually isotopic to the spun knot. So this is another way to see the spun knot, which is always ribbon, as opposed to twist spun knots, which are never ribbon. But anyway, it was Sato who introduced virtual crossings to all this. I don't think virtual knot theory even existed when Yajima was tubing things, but now if you have a virtual crossing, you just tube it to not a crossing, right? And that kind of virtual crossings are like you get to the other side without crossing, right? So it's kind of a nice manifestation. And this is, you're not touching in R3 where the diagram lives. Also, it's isotopic to having this one that looks like it's in behind, actually in front. So that's nice. And if you do welded moves on your arc or whatever, those correspond to isotopies of the tube surface, and every ribbon surface is a tube of something. You can do graphs for higher genus if you want. I think Kaufman was the first to do that, but I haven't seen much about it other than that it can be done. To me, it's really just a shorthand for a ribbon presentation, so that you don't have to draw these big pictures. But there are some interesting relationships with properties of welded knots being reflected in the ribbon surfaces. So there is some really cool stuff out there. And yeah, so we proved something about the meridional rank, the bridge number for this, and maybe we know something about that. In particular, the meridional ranks are the same because they have the same groups and the same meridians. Bridge number, not so clear, but when we do prove the meridional rank equals the bridge number for this welded thing, then we also get that it's equal for the knotted surface. So that's nice. Okay, so now it's time to start to get to talking about our results. It's kind of a lot of background because there's a lot of different kinds of objects here and different kinds of bridge numbers, and I just it's hard for me to keep it all straight, so I had to write really thorough notes about it. Hope that I'm not boring anyone, but I really don't care if I am. Anyway, a little bit of late night humor. So when does the meridional rank equal the bridge number? So this will be some times that we can prove they are equal for knotted surfaces and for welded knots. So we started calling these BBKM links for Bader, Blair, Kuchikova, Misev, because they found these really big families of links where the meridional rank is detected by a Coxeter quotient, and the bridge number is detected by the Vertinger number. So using the Vertinger number, they get the upper bound, and using the Coxeter quotient, they get the lower bound. So, so this first family I'm going to talk about is called twisted links, and I'm just going to show one by example. And this construction, by the way, is due to Brunner. So you start with a simple planar graph with edge weights, at least 2, and then so this is my simple planar graph. Now you dualize and get this blue graph, and now you plumb together twisted bands according to the edge weights, and you get some link. And this link is manufactured to have a nice Coxeter quotient that you can read off from the graph. So that's really cool. And what's even better is that it's known, so Coxeter groups, they all have rank 2, but or at least this one does, but we're sending meridians specifically to reflections, which it's known that you need at least 3 reflections to generate this Coxeter group, for example. And so in general, it'll be the number of generators in this specific kind of presentation coming from this kind of graph. So that means you have a surjection like this, your meridional rank is at least 3. And you can see this is a pretzel knot. So twisted links include pretzels, but they're much more general. And I mean, start with, so any cycle will be a pretzel, and you can start with any simple planar graph. So so this is a lot of knots and links. And like I said, Bruner developed this construction to get the lower bounds, but it was the upper bounds using the Verdinger number that that BBKM established. So that's family 1. Family 2 is these arborescent links, which are associated to trees. And I'm not going to explain how, I'm just going to show a picture of one. Yeah, so there's a lot of those too. And so here's theorem 1. If K is any BBKM knot, and you do any even twist spin of K, then its meridional rank does not change, and neither does its bridge number from the classical knot. So they're all the same number for the classical knot and the twist spun knot. And if you take K to be in this fancy KPN family I haven't defined yet, then you can do other kinds of twist spin. So this was only for even. Now P can be any integer. So you can get odd twist spun knots with nice quotients. And one side note is that so this is really confusing and obnoxious to explain, but bridge trisections are this other way of looking at knotted surfaces that are pretty new and popular. And they have their own bridge number, which is not the bridge number of the knotted surface. So it's very confusing, but I'm calling that just B for bridge trisection index. And that, so there's another parameter called the patch number, which corresponds to, is equal to the bridge number, the way I defined it. And so the patch number will be this beta, meaning the knotted surface bridge number, and then the bridge trisection number will be 3 beta minus 2. So Meyer Zupan asked in their bridge trisections paper, the first one, when is that true? When you do a twist spun knot of bridge index B, what do you get for the bridge trisection index of the twist spun knot? So for all these cases, we can say you get like the expected thing. Also, in the even twist spin case, the result also holds for connected summing copies of a standard RP2. And so this reproves a theorem of Sato and Tanaka. See, because of Euler characteristic reasons, you're only getting 1 mod 3 in the case of genus 0 surfaces. So if you want to get 0 and 2, you can take something so that you can still detect that the rank didn't change in the bridge number when you connect some on a standard RP2. So the even twist spinning is compatible with that, and that's because we're detecting these values by Coxeter quotients, which So let's go through the proof. This is the proof of one. You have this Coxeter quotient G, and notice that a meridian here, well, the square of a meridian dies because all the reflections are order 2. And if you instead first send x squared over to the twist spun knot group, since this makes x to the 2m commute with everything, that's compatible with the quotient. So the Coxeter quotient factors through the twist spun quotient, and you can kill x squared, or you can first make x to an even power in the center, and then you can kill x squared, and the result is the same. So when you connect sum and RP2 on, that just actually kills the square of a meridian. So that's also compatible with the Coxeter quotient, and that's why this part's true. So so this is really just an observation that Coxeter quotients are good for even twist spins. And here's a lot of knots that have Coxeter quotients. So 2 says something about odd twist spinning, which was a little bit harder. So we need a different kind of quotient because, you can't go killing a meridian squared and expect to have an odd twist spun knot be compatible with that. So what we figured out was how to label by p cycles in the alternating group. So you need to make sure that the p cycles used actually generate that alternating group, and you need some statement about how many p cycles are needed to generate. So this was a theorem of Anine and Maglione that I'm not going to state because it's a little bit technical. So there's some details to this that I'm not going to tell you about, but I will give sort of a small idea. So here's a twist box of 2p minus 1 crossings. In this picture, p is 3, and this is sort of what happens in general, coloring by p cycles. It's meant to show that what you've labeled by 1 through p at the bottom left is the same as the label at the top left. And if you go through and check the other labels, this one at the bottom right is the same as the one at the top right. And so that means you can, close it up, or you can attach it to other things that are also labeled by p cycles. So this KPN is the knots which can be labeled by n p cycles from that alternating group, because that makes everything work out nicely and tell you that, so this number, this mu of k and all these other things is equal to n plus 1. So an example, the simplest example is T25 is in K31. You can color it with 3 cycles in A5, and I did that. Isn't that nice? So you need, unlike in the Coxeter quotients where everything is its own inverse, you need to take orientations into account. And then connect summing copies of this with itself. You get into K3n, so that'll have Meridional rank n plus 1 because of these quotients. And now you can do any multiple of P twist spin of something in KPN. And you'll establish that the Meridional rank and the bridge number of those are both n+1. So that's what we had for alternating for odd twist spun knots. And you can piece together more complicated rational tangles, which are all p-cycle colorable to get, you know, more complicated things than just connected sums of T2 2p-1. But I didn't draw any more pictures of them. So next, I'm going to define, so this is getting back to the welded stuff, which we call virtual BBKM links. Maybe I should call them welded, I don't know, but whatever. Here's 3 moves you can do. You can take a crossing, make it virtual. You can flank a crossing by 2 virtual crossings. And you can do a flank switch, which is where you flank it and then also switch the sign of the crossing. So great. So theorem 2 is going to use these moves. So let L be a BBKM link with Meridional rank and bridge number n, realized by some Coxeter quotient G, which automatically exists because it's a BBKM link. And let L prime be any link obtained from L by a sequence of these moves. So in your twist regions, at the bottom, you either have both meridians the same or different. So if you have a region with only one Coxeter generator in your, you know, not necessarily meridians, but in your labeling by the Coxeter group, if these are the same, then you can virtualize any number of crossings in that twist region. If the twist region has 2 distinct Coxeter generators here, then you can, if there's an even number of crossings, you can virtualize some number, any number of the crossings. So that's 2. 3 is perform flank switch moves anywhere you want at your leisure. And 4, we call balancing out by adding a classical crossing after performing a flank move in a twist region of a rational tangle corresponding to 2 Coxeter generators. So it's kind of a mouthful, but it's a bunch of things. If you start with a BBKM link, you can do any of these things. And what's nice is you will not change the bridge number or the Meridional rank. It'll still be n. So here's that arborescent link from before, arborescent knot. And I did some of these moves. So this is the type 1 virtualization because these are labeled the same. This is the type 2. I didn't label them, but I just remember that these are different labels. And so that's the type 2. And then this one, we had 1, 2 positive crossings. Now we have positive, virtual, positive, virtual, positive. So this is that thing about balancing out after doing a flank move. So that's type 4. And then this is the flank switch. So this is 3. Notice this is the example I showed earlier. And it's kind of a fun example because the group here is a semi-direct product of Z3 and Z. And this is also the group of the 2 twist spun trefoil, or any 2 twist spun 2 bridge knot with determinant 3. But you can also get this kind of a more geometric way, looking at the tubes. So if you like cut this arc here, so now you're looking at an arc for the trefoil and tube that, you get the spun trefoil, and then you can attach a handle, a one handle stabilization to the spun trefoil to get this welded knot. And you can do that with any 2 bridge knot to get a welded knot whose group is any twist spin of that 2 bridge knot. So, you know, this is well known, but just kind of having fun with examples. So we get this with welded knots by the flank switch move. And the theorem says that we should still have a nice Coxeter quotient. So the natural Coxeter quotient for the trefoil is actually the dihedral group. And so this is everybody's favorite tricoloring. And so this theorem says that I should still have a tricoloring here, which I guess since I wrote the group down, you can sort of cheat and see, yes, that surjects onto D3, but it's more fun to do it this way. And there you go. We still have our Coxeter quotient, therefore proof by example. No, really. So I'm not going to prove it, but the outline is to show that these moves do not increase the Vertinger number. So this kind of speaks to how useful it is, the Vertinger number, and also it was important to know that it's equal to the bridge number to be able to use this kind of argument. So the bridge number is at most this number n, and then also show that we still have a Rankine Coxeter quotient. So it's at least n. So I think this is pretty cool and kind of just, I mean, BBKM links were already a big family, and now it's a bigger family of welded links that we still know the answer. So it's sort of just things work out. Both of the things that need to work out nicely do, and we can make a lot of calculations. Okay, so that's the first main section of results was just when do we know that these are equal? And now the last part of the talk is behavior under connected sum, or sometimes they might not be equal. So these are the examples that I think are counterexamples, but I don't know how to prove that. So just to say, there is an example in the literature that I found a long time ago. That's this old paper of Toru Maeda, and he was working with abstract knot groups. So it's like the group and a meridional class, and just working with Vertinger presentations. And so these 2 knot groups have 2 generator, 2 related Vertinger presentations. And so with, meridians as generators, so their meridional ranks are 2. And then he does the connected sum. So you G1 star G2 and amalgamate the X's. And then he plays around with the presentation and shows that that also has Meridional rank too. And what's striking is that he finds a Vertinger presentation with those generators, with 2 Meridional generators. But to do that, he has to introduce a bunch more relations. So, you know, if the bridge number actually does deteriorate, then you get a Vertinger presentation for the connected sum. Not clear that you can do that from his construction or from what I'm going to tell you now, but still it's interesting. And so since they're 2 generator, 2 relator, you can build a welded knot or a ribbon torus with that group and connect sum them and get a genus 2 surface where your Meridional rank is still 2. But we're now going to do it for knotted spheres, genus 0, and we're going to show that any value between the theoretical limits can be attained. So what are the theoretical limits? Well, if you have K1 and K2, so I didn't say this, but welded knots don't really have a connected sum operation. If you want to connect sum them in a way compatible with the tube map, you just put a little arc between them and then you have a graph. But I'm thinking, so this is true for that case, but I guess I'm thinking of knotted surfaces here. So the Meridional rank of the connected sum is bounded below by the maximum. That's because you can surject onto either the group of either factor, and it's bounded above by the sum minus 1, because that's sort of the obvious thing you get when you write down the amalgamated product. So that's basic stuff, but we're going to connect some n copies together. So this minus 1 on the right happening for connected sum of n things will be a minus n minus 1. So the theorem says for any p's and a q, which is at least the maximum of the p's and at most the sum minus n minus 1, you can find 2 knots, so knotted spheres with Meridional rank of Ki equal to Pi, and such that the Meridional rank of the connected sum is equal to Q. So here is the conclusion we can draw. Either the bridge number is equal to Meridional rank and therefore also fails to be -1 additive, or these are examples where the Meridional rank is strictly less than the bridge number. That's what I think happens. But you need something stronger to detect it. Like I was alluding to earlier, you could say, what's the smallest number of meridians in a Vertinger presentation? That's a little bit stronger and still a lower bound for the bridge number. And it's not clear to me that you can get that to be Q. But also seems hard to prove that you can't do that. So anyway, let's just go on with it. So the lemma, which I think, well, so the lemma is kind of a special case of the theorem. And I think it's sort of the most interesting special case in a way. So you're gonna start with all these 2 knots of a specific form. There'll be twist spun 2 bridge knots with coprime twist indices. And each one of them is Meridional rank 2, and so does their connected sum. So this is for any number of factors. So let's talk about why that's true. So these little k's, those are the classical knots, and those they're two bridge, so they have two generator, one relator, running representations. And then when you do the twist spin with twisting index mi, you can add this one relation. This is equivalent to the twist spin relation I said earlier, but it's a little bit more convenient for what we're doing. And so if T is this big connected sum, we've got all these X's and Y's for the different factors, and we have to amalgamate a bunch of them together. So the usual thing is just to amalgamate all the X's, and then you've got, maybe just call that X, and then X and Y1 up to Yn definitely generate. But that's n+1 things, and we want it to have 2. So let's see what happens with n = 2 as a easy case. So in this case, we're going to be able to do it because it's so small. So let's do a real example. So the mi's, let's say they're 2 and 3. Those are coprime. So this means if I do y1 squared, that's the same as x squared. And if I do y2 cubed, that's the same as x cubed. Oh, but look, 2 and 3 are coprime. So if I do y2 cubed times y1 to the -2, I get x. So I didn't need any x's. All I need are y1 and y2 to generate the group of the connected sum. So that's like the seed idea for what to do in the general case. But there's still this issue of amalgamating. Like if we do it like this, then I do claim that no two of these meridians generate. And that is a true statement because they'll just generate their own factor. So you could write down a meridian that's not one of those, and that would maybe work if you're careful. But I thought of a way I like better, which is to amalgamate in a zigzag pattern. So I'm going to amalgamate x1 and x2, y2 and y3, x3, x4, and y4, y5. And notice here, it was the ones being amalgamated that we could sort of get for free as a combination of the other two. So that means I should take y1 and x5 to be my generators. And so the claim is that, let's see, how much room do I have? Claim is that the subgroup generated by y1 and x5 is the whole thing. So we need some twist indices. So let's just say 2, 3, 5, 7, 11. And maybe you can sort of guess what I should do. So if I can show that I can get y5, then by induction, I'm more or less done. So what happens if I do y1 and I'm going to raise it to a giant number? It's going to be 2 times 3 times 5 times 7. Yeah. Versus, okay, so let's talk about this first. So this is equal to x1 raised to that power, because the exponent is a multiple of 2. x1 is the same as x2. And so it's the same as y2 raised to that power, the same as y3. And we're raising it to a multiple of 5 as well. So this is equal to x3 raised to that power, which is equal to x4. And since we're raising it to a multiple of 7, is also equal to y4 raised to that power. And y4 is the same as y5. So I'm just going to write y4, 5 raised to this big number. And x5 raised to the 11 is equal to y4, 5 raised to the 11. And 11 looks like an equal sign. (11) is relatively prime to that exponent. So there's some way of getting y4, 5 as a combination of y1 and x5. And now that we've got y, there is one like tiny thing to say about proceeding by induction, which is that there's an odd even thing about whether or not I'm taking a y and an x or a y and a y. So now that I've got this one and therefore also this one, I'm going to take x4. Well, I'm going to next try to generate x4, but in an argument by induction, it's kind of annoying because there's this, I didn't reduce the case really, I reduced it to the other case of having a y and a y. These would be the two generators if I just had the first 4 factors. So anyway, I think it's more fun than coming up with some complicated meridian and trying to see if it generates. But I know how to do that too, and I'll make a remark about that at the end. So let's talk about the theorem. This was just the lemma. So first, let's just call T sub I to be these things in the lemma, these T sub I's. So twist spun 2 bridge knots, and we're going to want ones of a special form. So we're going to need a lower bound to help us out. And so you can either use the MI twist spun T2 MI torus knot, which has a nice lower bound coming from the Alexander module, or you can use the MI twist spun T2 to MI minus 1, or other knots in this KMI, 1 thing, and use the alternating quotients that I mentioned earlier. Either one of those is property that if you sum the same knot in that family n times, you're going to get a meridional rank of n plus 1. So that's really what we need. And the idea, the K's, which were the 2 knots with the meridional rank PI's, that we're connecting summing together to get the Q. So the KIs are going to be some combination of these T's such that when you stick them all together, some of the T's group together in a way that raises the lower bound sufficiently high to Q. And at the same time, you have to be able to rearrange them so that you can group them together as a connect sum of different J's, where these are like the co-prime things, co-prime twist spun knots, and apply the lemma. So the lemma says that you can have any number of those, and as long as the indices are twist prime or co-prime, the Meridional rank of the connected sum is 2. And then we'll be taking some number of those put together, and by the lower bounds we have either one of your choice, you get n plus 1 for the Meridional rank of a term that looks like this. So that's the idea. So here's an example. One second. Okay, so here's an example. I think this is more illustrative than writing down the full argument. So my P's that I chose were 10, 8, 5, and 3. And then I chose Q to be 19, which is at least 10, and I shouldn't say 26 there. It's allowed to be at most the sum, which is 26, minus 3. Because there's 4 factors, so 3 connected sums happen, goes down by 1 every time. Okay, so there's this annoying like +1 thing with all of the lower bounds. So first subtract 1 just for my own sanity. And now K1 is going to be 9 copies of T1. K2 is 7 copies of T1. K3 is 2 T1s and 4 T2s, and K4 is 2 T3s. So let's check that they have the Meridional ranks we want. So 9 of these has Meridional rank 10, 7 of these has Meridional rank 8. For this one, you want to group it in a nice way. So there are 2 copies of this connected sum, which by the lemma, this by itself is rank 2. And so 2 of them together is rank 3. And then this one is also 3. And so then put those 2 together and subtract 1, you get 5. That's what we wanted it to be. And the last one, we just have 2 of those, so you get 3. Good. Okay, so now I'll put them all together. And the connected sum, we combine like terms. We have 18 T1s, 4 T2s, and 2 T3s. So for the lower bound, you can just surject onto the group of 1 factor and just forget those are even there. And you get, since your lower bounds are additive, you get for 18 copies of it, that your Meridional rank is at least 19. And now to see that it's at most 19, you want to group them in a more crunchy way. So you group together all 3, as many as you can. So there will be 2 of all 3 together, and then as many as you can of T1 and T2. So that will be another 2 of those. And then you have 14 T1s left over. So the lemma applies now to each of these 3 guys. And so 2 2s is a 3, and same thing there, and then that's a 15. So altogether, the rank is at most 3 plus 3 plus 15 minus 2, which is 19. Okay, great. So that's just kind of to show this rearrangement idea, which I'm going to make a remark about this now. These examples and this rearrangement idea are due to Kananobu, who introduced these examples in order to prove an analogous statement for the weak unknotting number. So this was the minimal number of one-handle stabilizations needed to abelianize the knot group. So it's weak because it's just like an algebraic version. So he showed if you take a bunch of examples like this, you can, in terms of dilemma, you can have these T1 up to Tn, any number of factors, and then attach a single one handle. And after you attach this single one handle, the group of that knotted torus is Z, but it's not so clear that it's the unknotted torus. You would have to really get in and show that geometrically. So Kananobu stopped there and was like, well, I can abelianize the group with one handle. That's pretty cool. And then he used that lemma in a similar way to say that for a connected sum with the PIs and the Q, you can get anything in between. So all that grouping and stuff is his work. And the reason I am familiar with these examples is we were considering them well, we wanted to see if we could smoothly unknot it, and basically we couldn't, but if we were willing to add one additional handle, so you get something like this, it will necessarily be trivial because the group is Z, so you can't do any funny business. That this actually is an unknotted genus 2 surface. And one note about the relation is when you do a stabilization like this, you identify two meridians. So there's some meridians X and Y, and you make them equal, and that abelianizes the group. Now, in this other project I mentioned, which was with Mike Klug, Benjamin Ruppick, and Hannah Schwartz, we showed, right, like I said, you can smoothly unknot it with an additional handle, and an analogous version for the Cass and Whitney number, which is number of finger and Whitney moves in a regular homotopy to the unknot. So the relations for a finger move force two meridians to commute, which is weaker than being identified. And we showed that actually, if you make those two meridians commute, you also abelianize the group. So I was already very familiar with them, but I didn't really think the meridional rank could deteriorate that much. It took me a long time to sort of really try hard to prove that. And so what we did is show that actually so there's two meridians. Kananobu said if you identify them, you get C. We said in this other thing, if you make them commute, you get C. And finally, in this meridional rank project, we showed that in fact, they just generate the whole group. And so if you think about it, if you have a set of meridional generators and you make one of them commute with the rest, that will abelianize the group necessarily because meridians are all conjugate. And so if one of them is central, then they're all equal and there's only one. So it's a cyclic group. So this was, I don't know, the name of that paper was like the weak unknotting number. And I wouldn't have gone to that originally to learn about meridional rank, but it turned out to be very useful. And I definitely think that if Kananobu was thinking about meridional rank, he would have proved that. But he was thinking about weak unknotting numbers. So anyway, I'm not like trying to say that it's something he missed because I don't think he was thinking about it at all. So anyway, it's just a nice thing to have found out. Anyway, thanks very much for your time and attention. And this was a lot of fun for me. I haven't given a talk in a long time, so I enjoyed this and enjoy the rest of your day.